All right, so we've written this down. Again, looking at the graph. Hey.
That was dangerous.
So looking at the picture, to find this area of this blue part initially would be like, that would be tough to do. But now, if you just realize you're taking the area under the upper curve minus the area under the bottom curve, that's all stuff you've done already, which is kind of nice because this is a review in that sense. We know how to do a definite integral. We can take the top one minus the bottom one, and you could do them together like this, which is nice when you can combine like terms, or you could do them separate, doing the area of the one minus the area of the other one. Visually separate really makes sense because that's like saying I started with the area of the whole thing, and then I took out my eraser. Well, I don't know if eraser's gonna. Maybe I'll use. How big is it? And then I erase this part, leaving me with just the area in between. That's the idea. Anyways, these are easy integrals to do. We plug in things and we get our answer. So, area between the curve, what does it do? Well, it involves knowing how the graphs look. So it's also a good review of, do you know what your basic graphs are? So you can tell which one is on the top, which one is on the bottom. How do you know you screwed up? If your final answer is negative, you know that you would have screwed up. What's the problem in a question like this? E minus 5/3 isn't intuitive. Is that a positive number or a negative number? Right? Not that easy without a calculator. So you did need to know which graph was on top and which one was underneath in this situation. Find the total area of the region enclosed by these curves. And again, something I mentioned yesterday, even though some of this area is below the x-axis, you don't have to worry about that for area between curves. We still need to find out what our two intersection points are. And we get them here. Oh, at this graph, negative 2, 0. Yeah, there we go. Negative 2, 0 and 2, 4. Those are our intersection points. And the area is just the top one minus the bottom one. And even though some of the area is below the x-axis, and that technically would be negative, it still works out. Combine your like terms in this situation makes sense. I think we did this exact same one before. And again, I know that you could do the mental math. In fact, do you need to do the mental math? If you wrote it out, if you plugged in 2 and you subtracted and plugged in negative 2, you do not need to simplify if this was a long answer on your AT exam. You could just leave that. I know that bothers people. Sometimes I do like having an actual answer. And sometimes you need on the AP exam an actual answer because you're going to be using it later on for something else. Getting the actual answer also can tell you if you screwed up somewhere. Because if I got negative 32/3, it means I didn't put the right function on top. I flipped them. So simplifying is still good because it gives you a chance to analyze your answer and see if it's reasonable. But again, on the AP exam, you wouldn't need to. So if you're super confident, you're like, I got this. I know I didn't make any mistake. You can just leave it. Find the area of the region in the first quadrant enclosed by the graphs of 2 cos of x and g of x equals x. make a diagram. So 2 cos of x, of course, this is your cos graph that would continue like this afterwards. You've got g of x equals x, so we need to find out where they intersect. Some things that are nice, this is a calculator question, so I'm going to pull up my calculator and show you a couple of things on here that I find are useful. Okay. Anybody realize why I'm about to get an answer, but it will be a problem? Anybody see it?
Be approximate.
2 cos of x and x. Those are my 2 graphs, right?
Yeah.
Okay. Anybody see an issue? I'm in degrees. Okay. Everything you do in calculus, derivatives only work in radian. Well, they work in degrees, but you have to do a chain rule and do a horizontal stretch compression, which you do not want to do in order for them to work in degrees. So make sure that your mode is in radians. I don't know if the AP exam would do this. If they would be like, I wonder how many students know they have to be in radians. So we'll set them up by making the last multiple choice question something that needs to be done in degrees. That would be a little bit mischievous, but good for us to know. Could happen, right? Do they do that on purpose? Sometimes they just do that and you're like, oh, we didn't realize that that would cause so many students problems. Make sure that we're in radians. Anyways, I hit graph here. I don't like my window, so I'm going to go zoom. I like zoom 6 is a nice one. I also really like zoom trig if you're doing anything with trig. There's our graph. There's our intersection point. But what I wanted to show you on this, so second calculate, number 5, intersect, enter, enter, enter. I get my 1.03. Did you know that anytime you solve something on a graph, it's the last thing you solved? So if I go second answer, it has that 1.03 built in. Okay? If I do any extra stuff in here, sometimes it disappears. So as soon as I go out of my graph, I like to take that answer and I like to store it. Maybe I store it as A, alpha A. Because now when I go here and want to figure this out, this integral out, this is a calculator question. I'm going to be going from 0 to 1.030. How can I be more efficient on my exam? Knowing your calculator well can save you 10 to 15 minutes on your exam in the calculator section, which gives you 10 to 15 more minutes to problem solve on the question you get stuck on. Right? They're going to have some tough questions you're going to get stuck on. Being able to be efficient earlier gives you more time that you can problem solve on those harder things. So here, what am I going to do? Okay, I want to find my integral from 0 to 1.3. I'm going to show you a couple of shortcuts. Okay, so I'm going to go to math. I'm going to go to my, is this my definite integral? Yes. I'm going to go from 0, and I have stored this answer as A, so I can put A in there. I can retype the whole equation, or I can go y1 minus y2 with respect to x. y1 was an equation with x, y2 was an equation with x. 1.184. Okay. On the exam, you are perfectly fine to go from this to this on a calculator question with no work shown. They will obviously assume that you did it with your calculator. There's probably no, because it's calculator, there may be no marks associated with the fact that you know that this is this integral, this is this integral. On a non-calculator, definitely They want to know that you know those integrals. But on a calculator, why waste your time with all of this when you can go directly from here to your answer? Okay? I'm curious. Right? 1.03 is rounded. It's rounded correctly to 3 decimal places. I can even put 1.30 in there. If I push enter there, do I still, I still get correct to 3 decimal places. But you have to be careful because sometimes rounding early, depending on the function, can really affect your final answer. And even rounding correctly to 3 decimal places early might not cause your final answer to be correct to 3 decimal places. In this one, you would have been fine. You would have been lucky. I talked about this one early last time. I'm going to highlight it with coloring here, not with a highlighter, my crayon. We have this orange section, area between 2 curves. And then we also have this, ooh, crayon was kind of thick there. That purple section. And in the orange section, the red graph was above the blue graph. And in the purple section, the blue graph is above the red graph. And we find our intersection points here. Okay. We make our 2 equations. It works out nice. It's a cubic. You don't have to use your synthetic division, long division, factoring cubics because it has a common factor of x. You get your 3 points, x equals 0, x equals -2, and x equals 1. And when you have 3 sections, you may have to do them in 2 different regions. Because if you just went from 0 to -2, or sorry, from -2 to 1, if we went from this point to this point and did one function minus the other one area will be positive and the other area will be negative. And when you add them together, you don't get the total area. You'll get an answer that's actually smaller than the orange area. So all we have to do is realize that. How do you realize that? You have to know what the graphs look like. How do you realize that if you don't know what the graphs look like? Just assume, oh, I have 3 points. It might be that one is higher than the other. And even if I don't know, again, if I screw up on setting this up and put the wrong one on top because I didn't know what my graphs look like, one of these areas will show up as negative, and then you know, oh, I put the wrong one on top. I need to make it positive. So you could just add absolute values all the way through and make your answer positive. So you have a way out even if you don't know which graph is on top. But if you're doing that, you would need to simplify all the way to the end to get your answer. And then your total area is just the 2 of them combined.
Units squared.
What's that?
Units squared.
Units squared.
No.
There's no units in this question.
Oh.
If there's no units, you could write units squared, but there'll never be a deduction from not having units on a no unit question. Yeah.
Do you think you could show you doing the absolute values ones for another author?
So that, let's say you did this and the idea is, what would it look like if I screwed up? And I just switched these two around, okay? So let's say you did that and you switched the two around, you would get -8/3 as your final answer. And you're like, uh-oh, I screwed up, okay? So what am I gonna do to fix this? I'm going to add an extra step where I say it's equal to 8/3 because I know it was supposed to be positive. And then to fix my work all the way through, there. I just added those absolute values all the way through. Like, I wanted it to be positive. I know I screwed up. It's not wrong, but it meant you didn't have to rewrite everything. So that's what I would do with the, if I realized, oh, I put the wrong one on top, I screwed up. Well, it's true if I put the absolute values. I haven't written anything wrong. Ideally, I've made it messier. But in my opinion, it would be way messier for myself to erase everything and redo it. That makes the solution nicer, but my life messier. So I'd rather just make the solution messier and my life easier.
Where's this?
So you can, this is the same question, just saying if you had a graphing calculator for this question, you could type one equation into y1, one equation in y2. You could go from this step right to there, no problem, and write your answer. So I could type 1 into y1, 1 into y2, find their intersections with my calculator, then break it up with y2 minus y1, and then y1 minus y2. Get my answer right away. Okay. Dangers of graphing calculator is you won't notice if you did the wrong things with positives and negatives. You'll just get a final answer and go, oh, I think that's correct. Which, again, if you showed this work and then just said I use my graphing calculator to find the answer and your answer is wrong, there's potential you could lose a lot of marks on that question, depending on the marker. The marker's like, well, there will be allotted a lot of marks for this and you obviously haven't got the right answer and have no work shown because you used your graphing calculator. So just a little bit of saying what you typed into your calculator, then they might go, oh, you just flipped those two. Maybe that's only a 1 mark mistake. We still know you know what you're doing. Again, thinking of this from just last year when you guys were in grade 12 pre-calculus. Could you have drawn this? Yes. You knew how to graph sine. You knew how to graph cosine. Could you have found the intersection? Absolutely. You know when sine is equal to cos from your unit circle at pi/4. They're both √2/2. So you could have drawn this completely. But then I would have said, huh, I wonder what that blue area is. And you'd be like, no. Not even close to being able to have an idea of how to figure that out. But now, we can set this up. From 0 to pi/4 of cos x minus sine x. These are integrals that we can do. These values are on your pie plate. And we can tell that that area is exactly root 2 minus 1. Which I feel that by the time you got to AP Calculus, your viewpoint of what are nice answers has expanded. Because in grade 9 or grade 10, if you would have been, my final answer is 37 over 13, blah, I must have done something wrong. I was expecting 5 or 7. Those are nice answers. In grade 9 and 10, nice answers are like whole numbers. And by grade 11 and 12, you're like, if I get a fraction as an answer, it's nicer than some ugly decimal. And now you get a square root as an answer, so we're like, well, that's kind of nice in a way, better than some, like, I think our viewpoint of what's a nice answer. And these curves are crazy. And have something simplistic like just a square root as an answer, I find that kind of enjoyable and kind of amazing.